Welcome to Chapter 17, Section 4. We're going to be talking about electric power. So what we're going to do is we're going to differentiate between direct and alternating current. We're going to relate electric power to the rate that electrical energy is converted to other forms of energy. And we are going to calculate electric power and the cost of running electrical appliances. So there's really two types of current, okay, and we can describe them as alternating or direct. So direct current is charges that only move in one direction. So if you have any charge, okay, it will flow this way, and any other charges will also flow this way, and they will only go in that one direction. Alternating current, though, is a little bit different, okay? In alternating current, charges are moving back and forth. Okay, so now we have got a charge here that will move this way, and then this way, and then this way, and then this way. And it will keep going back and forth like that. Okay, so this means there's no net or total motion of the charges. So this charge, if it was in a circuit, would not go all the way around, okay? It's just going back and forth, okay? So this happens because the sign of the potential difference is constantly changing. So it would be like if you could take a battery and constantly put it in backwards and forwards, and you were constantly changing the direction of the electric field. So another way we can look at this is if we have direct current, which we also call DC, okay? It is going to send charges all the way around a circuit, okay? So things like batteries provide DC. So you want to make sure you realize that batteries are a source for DC current, okay? On the other hand, though, we have alternating current, okay? And the symbol for alternating current looks like that. Okay, and what happens here is instead of the charges going all the way around, right, we're going to get a charge here, and it's going to go here and there. Whoops, that didn't show up like an arrow. And then we're going to have a charge here that's going this way and this way. And the same thing is going to happen through our resistor, okay? We're going to get a charge that goes that way through it and comes out. And one here that's going this way and that way. And all of these charges all the way around are just vibrating back and forth. Okay, and they vibrate through whatever we have. So if this resistor was a light, it will turn your light on, and it goes back and forth and back and forth. So I should have mentioned, okay, that your wall outlets provide AC. Okay, so I missed that on the light set on the last slide, but an AC source, okay, is your wall outlet. Everything you plug into. Okay, so batteries and other things supply energy for charges to move, okay? So even our wall source, right, that's providing energy. So before we've talked about power, and power is the rate at which energy is transferred, right? So that was before we were talking about joules divided by time, okay? So we can also then discuss the power or rate that electrical energy sources transfer energy to the charges to do work. So the way that we do that then is we can use these calculations, okay? So this is called electric power, and it is the rate at which charges do work. Okay, so we have this original equation where power equals current times the change in voltage. Okay, and most of the time we're just going to start dropping this delta sign, so it's P equals IV. Okay, and we also know that V equals IR, so we can also write both these equations as P equals I squared R, or P equals V squared over R. So these are just the same, really, as this. Okay, they're ways to calculate the power from an electric circuit. So it's our electric power. So let's go ahead and look at a quick example of this. So we have a 1050 watt electric toaster, okay, and it operates on a circuit in your home at 120 volts. What is the resistance of the wire that makes up the heating element of the toaster? So what heats the toaster up? Okay, so we need to think about the things that we know. We knew from before, okay, we got to think back. Watts is a unit of power, okay, this is our watt. It's the unit of power, so review that if you need to. So we're going to have P is equal to 1050 watts, okay, and then we've got 120 volts, so that's V for voltage, so we know our potential difference is 120 volts. And it's asking us for resistance. Okay. Okay, what is our resistor? So based on that, we got to think about the versions of the equation that we have, right? And so the versions that we had are P equals IV. Well, we don't have current. Okay, we had P equals I squared R, and we had P equals V squared divided by R. Okay, so in this case, we have V, right, and we have R and P. So we're going to want to use this version of the equation. Okay, so P equals V squared over R. So now I just need to plug in my information. So I know the wattage is 1050 watts equals my voltage squared, 120 volts, squared over R. Rearranging and solving for R, we get R will be equal to 120 volts squared over 1050. Gives us our resistor is equal to 13.7 ohms. Alright, so that's the end of this section. I'll see you guys in class, and let me know if you have any questions.